Hi, fellow geochemists and geochemistry enthusiasts. Welcome to GeoChemISTea, the only podcast for people who love geochemistry with a side of tea. Our mission is to inspire future geochemists and to introduce our listeners to niche geochemistry topics. I'm your host, Sam Scher, and this month we're talking with Owen Missen about cobalt cycling. Today, we're joined by Owen Missen, a lecturer in environmental geology at the University of Tasmania and a researcher with CODES. Owen's research focuses on the environmental geochemistry and mineralogy of critical elements, including cobalt and tellurium, with an emphasis on nanoscale mineral phases, metal cycling in soils and regolith, and the environmental impacts of mining. His work combines field studies with advanced analytical techniques to better understand how metals move and persist in surface environments. Owen, welcome to GeoChemistry.
Thanks for having me, Sam. It was good to meet you last year at the SEG conference in Brisbane, and now good to be chatting with you, even though we're on opposite sides of the world.
Yeah, I love this. I love also how sometimes people are just like, hey, we met 4 months ago. Let's do geochemistry. And I'm just like, absolutely. This is amazing.
Yeah, it's really good to be here.
I love it. So, Owen, can you tell our listeners a bit about how you got into geochemistry?
Yeah, absolutely. So I was really a chemistry nerd initially. I loved the weird elements of the periodic table. That was what got me into geology and geochemistry in the first place. And initially at university, I was studying chemistry and thought that was the way I wanted to go. But increasingly, I just couldn't quite see the interesting jobs in chemistry. But I could definitely see when I went to do some extra geology courses, that was actually much more exciting, or getting to go do field work, do all those kinds of things that geologists get to do. And chemists typically don't, maybe go to a plant, but nothing else quite so interesting. So I thought I'll make the jump and moved across to do some mineralogy of tellurium, which will become a theme later on in today's show, and just fell in love with it. And suddenly I was here doing a PhD on tellurium biogeochemistry. So really it was the love of these strange elements in the periodic table. I thought chemistry would be the way to look at that, but it turned out that geochemistry was the answer.
Maybe we're jumping here, but what in particular about tellurium here got you into, you were just like, tellurium must be a geochemist?
I think it was the number of minerals that it formed. It was just, it's such a rare element. Like it's, I don't know, 1 part per billion, so you're down at the gold, platinum kind of levels of abundance, but it forms nearly 200 different minerals. So that just got me so intrigued. I was like, how does this one tiny rare element form so many different things in nature? And that was what really got me hooked in.
I love that. And now you've made a career out of that.
Yep. It's
Guys,
been very lucky to follow along.
Opportunities here are endless for geochemists, it seems. I love that. I've never, so working in exploration and in the mining industry, obviously tellurides and sulfur salts can all be a big thing. And it's not that I haven't noticed tellurium hanging around. Yes, obviously. I just never really thought about it in that context. And that's so cool and cute that you fell in love with tellurium. It's so cool. We should move on. So look, before we get into cobalt, tellurium, all the nanoscale details, we like to start every episode with tea time. And this is where we invite our guests to spill some tea. So what have you brought for us?
What I've brought for you today is a bit of a story about Tasmania, which is where I'm living now. I grew up in Melbourne and now I've moved down to Hobart in Tasmania. It's Australia's southernmost state, for those of you that haven't been down to Australia before. And it's got this image of, oh, it's always lovely forests, cute animals, come down to get some fresh air and come and have a beverage or two on the coast and enjoy the scenery. But really, Tasmania has been built on mining, like many parts around the world. But people today in Tasmania, even now, might forget that's the case, because most of the mines are hidden over on the west coast of Tasmania, some 4 or 5 hours drive away from the main centres of Tasmania. So it's a little bit hidden, and it's in this wonderful forested area. And you've got these volcanic belt, Mount Reid volcanic belt, and quite a few very large mining deposits. Tasmania's legacy, unfortunately, despite that image of natural beauty, is quite questionable. There's over 700 contaminated sites across the state, And one of the most infamous is the Mount Lyell area, which was a copper producing mine district, and it's been producing copper for over 100 years. So the site is currently in care and maintenance. Now, what's been happening out there was that the mine was designed to have riverine tailings disposal, which anyone in the know, that's probably not the greatest system in the world, because you just end up with the waste being flushed down and it doesn't go into the ether, it does end up somewhere. And in Mount Lyell's case, that mine tailings has ended up down in a place called Macquarie Harbour. So it hasn't got all the way to the ocean, ended up in this harbour that's on the west coast of Tasmania, and there's a very narrow entrance out to the ocean a little bit further over to the west. If you look on Google Maps and go zoom in on Western Tasmania, you start seeing this orange smudge. It looks impressive from the atmosphere, but it's not really what you want to be seeing, because what you're actually looking at is the oxidation of pyrite, or iron sulfide, as we all know. And that's basically this fairly impressive delta that really shouldn't be there. So it's one of these sites that we'd much rather didn't exist, but it does. And that cleanup operation, if it was to occur, would run into the probably billions of dollars, I would imagine. So it's this mine waste storage. We now hopefully mostly have tailings dams or other ways of storing the mine waste that's being produced. But in this case, for 80 years, up until 1994, the year I was born, which makes it feel relatively recent, we've got the Mount Lyell tailings just sending down the Queen King River and ended up at the delta in the Macquarie Harbour. So you've got all this tailings ended up down in the Macquarie Harbour. And that's a spot now where there's being salmon farming done a bit further down the coast. And you've also got an endangered species called the Maugean skate that lives in the harbour too. But the mine waste often isn't mentioned as much as salmon farming in terms of potential environmental risk, but it's sitting there, it's slowly oxidizing, but for now seems to be, at least on the surface layers, relatively stable, but underneath that you'll be finding lots and lots of unoxidized pyrite. At least it's 1994, the tailings were put into a tailings dam, but for a long time before that, it was coming down the river, and there's still acid mine drainage off the site coming down the river today. The interesting thing about that too is that the state government actually owns the legacy. They agreed to take it on so that the operation there could continue, because no company would otherwise be willing to take it on. So it's one of these interesting situations where you've got the state government owning the legacy of how the mine was operated for 80 plus years, and now the current operators only need to be responsible for what they are doing currently. And that is the one. You've found the exact spot now. So it is fairly easily visible if you zoom in.
Yeah.
There is a delta at the south end of the harbour too. That's the Gordon River Delta, which I think is the sand. As far as I know, this one is the pyrite. But it's interesting, there is actually another one down there. Probably sand. I haven't actually been to that one to check. I should go have a quick look and see it's not pyrite as well. Who knows?
So everybody, I've looked this up on Google Maps. Super easy, because you just type in Tasmania, you go to the west, and then you can just zoom in. I first saw the delta out of the Gordon River, which we were just talking about, and it does look like these cute kind of little sedimentary ripple formations. Owen needs to go down to check it out. But going a little bit further to the north, probably a lot further to north.
It's 20 or 30 kilometers, not too far. Yeah.
Not too far. But yeah, going up and looking at the King River, it is shockingly orange, and definitely not something that I would have ever thought of, because deltas can look really weird. I guess most of them now are probably just polluted anyway, but that's really fascinating. The whole history behind it, number one, but then just that it's just sitting there, potentially incubated, but definitely looks like it requires some intervention here.
Yeah, definitely not completely incubated, but the surface layers at least certainly have oxidized. Going deeper down, you find that pyrite hasn't, and it's also the coastline there's definitely getting smaller with time. It's being eaten away by the harbour. There's waves. It can be quite wild in there, even though it's a harbour. You can get some pretty intense weather coming in, blowing off the Southern Ocean. As we often like to tell people, the nearest landmass, if you head out west from Tasmania, is South America. So it's a long way around. There's just waves come in and storms come in and can smash away at little Tasmania. And there's nothing much else to stop it for the rest of the earth. It's further south than Africa is. So this really wild part of the world, but unfortunately it's got that tailings delta there, and it's got the mine ore at Mount Lyell is about 20% pyrite, and pyrite was a waste product. It was once used to smelt the ore, but that stops, and more pyrite got sent down the river, which pluses and minuses. Stopping smelting on site was in that case a good thing. They didn't have sulfur scrubbers for a long time, which is not ideal either. The pyrite ended up in the waste, and you've got 20% pyrite, which does have some elements in it that we'll talk about later on in this show. So there's potentially some remediation that can pay for itself if you get all those critical metals out of the delta. But you've got that stabilization question. How do you go in and actually work on a site like this without causing potentially more issues if you create some sort of submarine landslide or so, if you're trying to dig out the materials, and it's not the most stable thing in the world to bring on really heavy earth moving equipment. It's essentially, it can shift, it can sink. So you've got these really interesting questions about how to go about remediating such a site.
I look forward to talking about this more. This is fascinating. This is great tea.
Thank you.
This is great tea.
Great, good, but
who
bad.
knows about, yeah, exactly. I think of, maybe not oyster, but I think of some kind of mussel farming or something. I don't think of, I mean, I know that there, because I work in economic geology, I know that there is a component of Tasmania that has historical mining and everything, but we don't think of it as like a mining powerhouse, or also a place that has a poor legacy of mining. I live in the United States, and I can think of these beautiful areas like that we have. Say, we think of Colorado and to the north, right? So beautiful, like the Rockies, and how gorgeous is this landscape. But the legacy of mining there has been also quite rough. So
it seems to be a story globally, really, isn't it? And it's historic, but also present. We still have 2/3 of Tasmania's economy exports just about coming from mining. So it's really actually running the state in a way that most people don't realize. It's not just tourism, agriculture, it's actually mining royalties, and mining profits are still paying lots of the bills to the state. So it's a really important part of the economy here.
Oh, that's interesting too. I didn't realize that. Huh.
Yep, still some good sites around. There's a really big tin mine, Renison Bell, polymetallic things like Rosebruce. There's all sorts going on the west coast. And if Mount Lyell gets back to production again, it's got a lot more copper in the ground. So there's some really interesting potential across the state to continue doing these mining operations, but with much improved environmental standards as we move forward further into the 21st century.
Of course. Excellent. I love that. Thanks for sharing. But I think, as you say, it does allow us to shift gears pretty easily into the next phase of what we're going to be talking about, which is where your work currently sits, really at this interesting intersection of environmental geochemistry, mineralogy, critical metals. But here we can ask a really simple but powerful question, which would be, how do elements like cobalt and tellurium actually move through the soil's regolith and ecosystems? So whether we're talking about legacy mine sites or the next generation of these critical minerals projects, the same challenges will come up again and again. If we don't understand the chemistry at the right scale, we potentially are going to be making still the wrong decisions. So that in mind, let's dig into your research. You want to give us a little intro before we start?
Yeah, absolutely. So as you said, my research is based on looking at particularly how elements move through the environment. And in my PhD and my first postdoc, it was much more about going to surface outcrops, and we'll talk about those quite a bit today. But now looking a bit more at what's happening within tailings dams, particularly in Tasmania. I've been part of a critical metal in Tasmania project for the last few years since moving down to the University of Tasmania. But what I've increasingly found is that just finding out the complexity of all these different systems, and you can't really study an element like cobalt or tellurium just by itself. That's initially what I intended to do with tellurium. You're looking at an element that's, even when it's enriched, it's still pretty rare. So you have to trace around other things like iron and sulfur, and also know what's happening for those major elements to be able to look at your trace elements. You can't really just cycle tellurium cycling in complete isolation as I'd hoped to do, because other things just keep turning up. And you're finding that you start asking questions about soils, and you start asking questions about regolith, and then you realize that actually you should be doing some microbiology too, which is something I knew absolutely nothing about, never studied biology at school before. So it was a complete jump into another unknown area, but does relate to geology. And that's one of the good things about geochemistry. You can put anything almost in front of it. You've got the biogeochemistry, you've got inorganic geochemistry, organic geochemistry, and all those things do come together in this sort of work.
That's amazing. We're not just satisfied being geochemists, because chemistry is not enough ever. But you can, as you say, add on those additional prefixes. So I guess first, let's look at some big picture stuff. Before we get into all of the science that we're going to be talking about today, could you start by explaining why cobalt is so important, both in terms of modern tech and why geochemists care about it, how it behaves in the environment?
So for modern technologies, cobalt is one of those elements that's seen almost globally as a critical element or critical metal, depending on your flavor of the month. Cobalt can be both. So it's one of those ones that's being found in battery technologies particularly, and the global production's just ticked over 200,000 tons of cobalt per year. So it's still increasing at the moment. And really why we need it is it's really good at being found in batteries. It can change oxidation state, and you can then use that to help store charge, transfer charge, move things around in electrical circuits. So you're looking at all your battery technologies, electric car technologies, those kinds of things. And two of the major places you'll find cobalt, lithium cobalt oxide batteries, or nickel cobalt manganese batteries as well. So there are two places where you might find cobalt. And increasingly, the vehicles that people are buying these days are electric vehicles, and they have very big, heavy batteries in the front of them. And cobalt's usually one of the driving metals behind there. It's got, again, the two oxidation states, the +2 and +3. If you don't have major oxidation state changes, it can't really be used to store electrical energy very much. But then you've got elements like lithium that can be used in terms of their charge transfer capabilities, because they're light, small cations that can be moved around through circuits. So different elements for different things. And that's really the story of the critical metals area. That's that they need lots of different elements to do different functions. They all behave slightly differently, and we need almost all the periodic table in some way. It's one of these really interesting parts of today's society, and we almost need every single metal out there. We've pretty much got to a point where you can just about find any one metal in any product. Phones are using some 70 elements these days, I believe. So you've just about got all of them in your hand, although you can't really drill down too easily to see where each one is, because they're often found in pretty small amounts. But we really are using the periodic table to our advantage. That makes some pretty complex supply chains. And for cobalt, looking at, it's mainly found in pyrite. It's one of the most common places to find it, particularly in waste pyrite. So it might not end up in the main production stream. But cobalt can be found in more than just pyrite. It's in a range of different geochemical systems. You've got things like epithermal, can be found in massive sulfide systems with nickel and copper. Can be found in laterites, where you've got the heavy weathering going on. You've got nickel cobalt laterites that can be found in places like New Caledonia. Even some carbonate hosted deposits. You've got the SED hosted carbonate, and with cobalt and copper, for instance. And then you've got all these different geochemical behaviors that can be occurring. We found mainly with transition metals. So you've got your manganese, your iron, your nickel and copper. And this is, again, chemistry and the terminology we use sometimes get a bit confused, because it's a transition metal, but it's nothing to do with transition of energy from more coal-fired and gas-fired to the more renewable sources that we're looking at today. It's about the transition from different parts of the periodic table from one to the other. So you're jumping across from calcium to gallium, and you've got all these metals in between that don't conform with what metals do in the first 20 elements. And suddenly chemistry gets a lot harder for high school students. You've got to find out what happens when you stick electrons into the center of metal and they add on the shells there. And that's where you get transition metals. And that's where cobalt's also found. Of course, it's nothing to do with transition to green energy, though. It's just about the chemistry of it. And that's where cobalt turns up. So it's in the middle of the transition metals, but it's also, because of these electrons and where they're found, it's really good at that charge transfer capability. That's why we need it.
I have learned more about cobalt, about batteries, about all the things in the last 5 minutes. This is great. Sometimes I ask these questions, so I'm just like, oh, like this is a general knowledge question. Not everybody knows everything like I do. A lie. Anyway, but in this case, I don't think there's nearly enough literature out there. I didn't even know that our lithium batteries in cars had that much cobalt in them, or that we had a lithium, manganese, cobalt. Maybe I should read more. Anyway, this
Yeah,
is
there's a
very
few
cool.
different types out there. So there's different
Yeah,
ones might not have all, but yeah, it's really interesting on how the elements being combined into different products to
totally.
help do charge transfer.
Yeah, I love it. Geochemists, we're so needed for everything. Whenever we don't feel relevant in talking with our like quote normal friends, we're relevant now because we've just listened to this and we can throw this little fun fact out at trivia night. I love it. So that was great. And then also general knowledge, because something we're going to be talking a lot about too today is nanoparticles. And you use this term a lot throughout your work. So for many of our listeners, we are likely not working on the nanoscale. So could you explain to us exactly what is a nanoparticle and how does it differ from the mineral grains or phases that we're usually maybe thinking about when we're working in our geochem data sets?
I think defining nanoparticles should be a simple question. It's nano size, but then even within that, you
Thank
have
you.
people that say different things. And so it's more complicated again, as most of these questions are. Some researchers prefer nanoparticles to only be less than 100 nanometers, but others will extend it out to 1,000 nanometers, which is the same as 1 micrometer. And that's the definition that I prefer to use. Just by definition, you're in a scale of nanometers where you've got singles, tens, or hundreds of nanometers in size, and that's the one I've been usually using. And so to put that in context, thinking about the scales of 10, so you know, most humans are on the scale of meters, with 1 or 2 meters tall in that kind of area. If you divide that down by 1,000, you get down to a millimeter, which is a size that we can still see on a ruler. You have that gradation between centimeter and millimeter. We mostly have an idea of what a millimeter is. Do that again, and we're down at 1 micrometer, another 1,000 times smaller, and by that point we can't see it. And a micrometer is about the size of the average microcellular organism, so bacteria, normally about 1 micrometer in diameter. So all those filters that you see for 0.45 microns, the main reason, or which can be described too as 450 nanometers, they're that size because they stop microbes getting through. So you've gone down below the microbial size, they can't get through that, and then you have a nice clean, hopefully bacteria-free water sample if you're doing water sampling. But if we're coming down through, we've gone through the 1 micrometer, we go 1,000 times smaller again, and we get to 1 nanometer. And nanoparticles of 1 nanometer in size are really very tiny. I haven't seen too many of those myself. I'm mostly looking in the tens or hundreds of nanometers. There's not much further to actually go. In reality, we think, oh, you can just keep going and going, but you can't. 1 nanometer. If you go down another factor of 10, you get to 0.1 nanometers, and that's about the distance of the bonds in a water molecule. And unless you want to go into particle physics, which I'm not really planning to today, that's about as far as you can go. So we're only about 10 to the power of 10 away from the atom scale. We can't, of course, zoom in and see it. We're looking at them all the time, but we can't discern individual atoms with our eyes. Quite sadly, I'd love to be able to, but that's the kind of scales we're looking at. We're looking at between factors of 6 to 9, magnitude of 6 to 9 order below the regular distances we're looking at. That's where we're down in the nanoscale. And that's smaller than what we're mostly looking at in geochemistry. Clay and silt particles are in the few micrometers range of order usually. And we're now looking below that size into the nanoscale. And it's a whole different world down there.
I would just say I think it would be distracting to be looking at the world in nano size. Maybe an extra lens that you could put on, but otherwise I think it would be a lens. I think that would be the way to do it. Yeah.
It would make crystallography much easier if I could see the atoms rather than having to do crystallography on the crystals.
Perfect. Practical. So once we're starting to think at the nanoscale, how does the chemical behavior and mobility of metals like cobalt start to change compared to bulk minerals or even dissolved ions?
Yeah, things really do start to change down nanoscale, and the main reason for that is surface area, because you have so much more surface area once you get down to nanoscale. A particle that's, let's say, 10 times small diameter than you've got in the same number of particles, you're suddenly looking at hundreds or more times surface area to interact with surrounding environment. That could be water, it could be other materials, it could be the microbes that are living nearby in an area, and these can all interact much more effectively with nanoparticles than they can with very large surfaces where you've only got a small amount of surface area involved. And you can go through and do these calculations, but it's really just about the change in area and even volume of materials that happens as you go down to a much smaller scale. You have much the same number of materials, but much more in terms of nanoscale, then you do have a great amount more surface area to work with. And this means that they've got much more chemical reactivity. Nanoparticles will be more reactive. They can cause different reactions to occur much more quickly. And they're also, by virtue of their small size, much more mobile. If you think about a river and sedimentology, it's much harder to push a boulder down a river than it is to push a silt grain down the river. If you think about nanoparticle, which is smaller again than your typical silt grains, that's going to be even easier again to move around. It just can really get pushed down by even a fairly small trickle, and that can be moved around the environment much more easily. So once you have nanoscale, you'll find that the mobility of things tends to go up. Reactivity goes up as well, even for compounds that may not be seen as quite so reactive in their macro form. If you only have a small surface area and only a few hundred atoms inside that particle, it may actually react quite quickly. And suddenly we're looking at quite different scales of behavior. And that's, at least at this point, beyond what we're mostly doing in geochemistry. It's still typically looking down maybe to the micrometer scale at the most, maybe a bit further if you're looking at crushing up a sample into oblivion before doing a 4-acid digest, but we're not really looking exactly what materials are coming out at that point. This is now looking to try and understand the behavior at the nanoscale more, and I think we'll definitely see a bit more of that moving forward, just to really get that full picture of what's going on down at the nanoscale.
Interesting. And following with that, looking at your recent work, you're showing that cobalt commonly occurs as these cobalt manganese oxide nanoparticles in soils and regolith. So in here, what was the key evidence that told you that this wasn't just dissolved cobalt or fine grained bulk mineral matter?
I might just step back a tiny bit even to start and just mention the study a little bit. So we were traveling
Yeah, let's do
around
that.
Australia. Yeah, let's do it. I'll just, before I jump right in, so
Perfect.
it was a little trip, I say. It was a trip around Australia with the funder for this work, was Dr. Stuart Mills at Museum Victoria, and we got some funding from philanthropy to go look at cobalt. So we thought, great, we'll go and find as many interesting sites as we can. And we looked at a map of Australia and picked out that there's lots of different deposit types around the place if you're willing to drive for a few days. So off we went. So we covered about 10,000 kilometers in 3 weeks in a Hilux and covered as much ground as we could to see all these different sites around the country, collecting soil samples, rock samples, and even some plant samples as well. While we're out there, it's much easier to get everything in one go than go back and do it again. As we all know, a single field campaign can be more productive than two if you get it right, ask the right questions. And we're looking in them, particularly the main interest was in the soils from the different deposit types that we found, and to see what behavior and what minerals and what elemental transformations were going on in those soils that we were finding around surface outcrops of higher than average cobalt. That included quite a few different types of sites, which I'll come back to a little bit later. But in terms of how we knew that there was actually cobalt manganese oxide nanoparticles in there and not just dissolved cobalt or fine grain sludge, everyone's favorite. But what we were using was a technique called single particle ICP-MS, which is a different type of the inductively coupled plasma mass spectrometry system. Many of you may know the laser ablation type, when you're ablating a mineral to work out the trace element concentrations and sending that through the mass spectrometer. In this case, what we're doing was making a suspension of the soil in water, then aspirating that into the machine. And then there's a particular add-on that can count the number of nanoparticles. This was being work done at the University of Graz by researchers David Clases and Raquel Gonzalez de Vega. They'll work on these samples for us, our collaborators, and they can actually count the number of nanoparticles in a sample now. So we're getting down to some really interesting techniques, and a few other people around the world are doing this too, but it's still a relatively new technique, only been around for, I think, less than a decade, might be wrong, but in terms of slightly wider applications, just working out how the technique works, it's been a relatively recent thing. So we can actually find out how many nanoparticles are in a given sample, and that's really exciting to be able to do that. You correct away for any dissolved material, so you're trying to ensure you're not just counting dissolved cobalt when that comes through the system, because inevitably there will be a small amount of dissolved material as well when you're trying to aspirate nanoparticles. Some of them will dissolve, so try and count that, and there's uncertainties associated. Also, that was the main technique for counting nanoparticles, but we also looked at the use of the ESRF synchrotron. This is a place in Grenoble, or European Synchrotron Radiation Facility. Synchrotrons, essentially giant particle accelerators but we don't even care about the particle acceleration that much. What we want is the X-rays that get sent off the side when you spin electrons around in a circle really fast. And we're using those X-rays to go down to really high resolution and look at the number of nanoparticles that we could see in the samples. The only slight challenge there was scale. We're still looking down at a level of microns, so a couple of microns we could see. So we're looking at the micron scale there, and we could see clusters of cobalt manganese in the samples. That was the way we could tell the cobalt manganese were clustered as well. But you couldn't quite see right down to nanoscale yet, but there are techniques being developed that will allow us to image the nanoscale as well. So we're really getting very close to being able to do these things. There's still some developments of techniques need to occur so we can see down to that scale even more effectively.
I think because I'm creative in some ways, but with this stuff, it always just blows my mind, like how people come up with these breakthroughs. It's really incredible. Wow.
I think the techniques themselves really are incredible too. I'm not a
Yeah.
technique developer. I'm able to use them to look at some really interesting questions about regolith behavior and what things are doing in the nanoscale.
Mm.
But yeah, without the techniques, we really don't have that much. As you said, we need a lens to be able to look at these nanoscale materials, and these materials and methods are the lenses that we have to use, but they take a long time to develop. So these method development things are really important as well. They're often the unsung heroes of what we end up doing.
Totally. Wow. Okay, so look, it turns out in this that manganese is pretty central to the story. So why is manganese so effective at controlling cobalt oxidation state and immobilization in surface environments?
Yeah, manganese is a really interesting element. I think I've probably said about almost every element, except perhaps the ones that don't change as much. But I really do love a lot of them. So manganese,
Nobody
it's
likes
got.
oxygen. It's fine.
I like when it makes secondary minerals, but that's probably a different story again.
Uh,
But manganese, yeah, it's a redox active element. It's got the different oxidation states. It's got the +2, +3, +4. They occur mostly in the environment. And if you, again, think back to your high school, you might remember some potassium permanganate, that beautiful pink dissolved chemical that is a very strong oxidant that does not occur in nature. So manganese is, yeah, it's really good at controlling oxidation state of other materials. It's quite good at sorbing elements like cobalt onto it, because it's generally present in a more of a bulk amount compared to cobalt. It's relatively common. It's about nearly 0.1 weight% of the crust manganese, so you've got a lot more of it than you do cobalt, which is only 25 part per million in the bulk of the Earth's crust. So it's generally found in higher amounts. And even though we went to a few different sites, that it wasn't just manganese rich around the manganese lateritic type deposit that we went to, there was also manganese in all the others as well, being associated with the cobalt. And perhaps we expected that might be an association with iron, but it was manganese that was doing all the work in terms of initially sorbing and then we think structurally incorporating with the cobalt to make manganese cobalt spinels. So these are the spinel, the most famous one, of course, is the better known mineral, but there's lots of different spinel structures where you can get different metals into these two sites, and cobalt and manganese can both go in and swap around with cobalt 2, cobalt 3, manganese 2, manganese 3. There seems to be more affinity for these two elements in terms of their ability to bond together compared to cobalt with iron for these structures. And we found that, yeah, manganese oxyhydroxides and oxides were just really good at binding cobalt, and that was the association that turned up almost everywhere. So it was a story that we intended to tell about cobalt, and in the end we told one about manganese as well.
Definitely in exploration, we have a problem with between the iron and manganese oxides of scavenging metals. So I guess overall, whatever scale it is, it doesn't necessarily surprise me, but interesting. Love it.
Yeah, I think manganese is, yeah, certainly one of those ones that just is a scavenger for sure. And we've manganese nodules in the ocean beds, another place for manganese to
Mm,
scavenges things. And that's potentially a source of these metals too, without having the technology probably to go and do any of that sort of mining. But it's definitely one of those elements that does scavenge things, and yeah, it can artificially inflate the concentrations too. I guess that's the problem with these things. Sometimes they're too good at their
that's a
jobs
big
and
problem.
screw
Yeah.
things up.
So look, let's return back to your little trek across Australia there. 10,000 kilometers in 3 weeks. Aggressive. Anyway, you looked at cobalt behavior across some very different deposit types. So sulfur arsenate, pyrite hosted, carbonate hosted, lateritic systems, etc. What surprised you most about how consistent the nanoparticle signal was across these environments?
Really was surprised that the nanoparticle signal was quite similar across the different environments. So there were more cobalt nanoparticles in places where the cobalt was richer, which did make sense. But just the fact that it was being found manganese every time, except for a few nanoparticles that were found at cobalt arsenide localities, a couple around Queensland where you've got outcropping cobaltite and a few other those cobalt arsenide minerals. So that there were a few more particles there that seemed to be cobalt arsenic based rather than cobalt manganese oxide based. But it really was surprising to find that was actually the behavior everywhere. We expected a bit more of a variety. Our initial hypothesis was different types of nanoparticles at different deposits, but it proved that wasn't the case. It was actually quite more uniform than we expected, at least in terms of the chemical makeup. The size varied a little bit. We had some small nanoparticles being found some places, larger in others. And that was really good. We could see that from the single particle ICP-MS technique, but it was quite surprising to find that cobalt manganese was the major association, and that then led us back to do some further work with the single particle technique, adding on a time of flight spectrometer as well, and that allowed us to see that yes, mostly it was cobalt with manganese that was being found at the nanoparticle signatures. There were a few other ones in there too. There's a bit of cobalt with titanium at times, occasionally, as I mentioned, cobalt with arsenic if there was enough arsenic in the deposit, but cobalt manganese oxide was the major type of nanoparticle that was being found in the environment. So that gives us some clues about where the cobalt might be going. As you mentioned, in the bulk, you get the scavenging occurring from manganese and potentially iron oxides. And it seems that at nanoscale, there's potentially also some scavenging going on of cobalt. It doesn't stay soluble for long. It appears to end up in nanoparticles, but they themselves can be quite mobile if you get that, say, pulse of rain that can push nanoparticles away from the initial deposit and get washed across the environment. That might be a way for things to disperse out that we haven't really considered that much previously.
So niche, but not at the same time. I love it. So your results suggest that cobalt may be more mobile in the surface environments than traditionally we've assumed, and this depending on redox conditions and nanoparticle behavior. What does this mean now for how we assess environmental risk around historic or active mine sites?
Yeah, I think that's a really important point, and often the regulations are a bit slower to follow compared to new results, new developments, and things. So it's what I expect we'll see will happen over the course of this century is that we'll see a bit more in the work in nanoscale remediation efforts about what's happening down at further scales where we can actually see that now. So we need to be a bit more careful about assuming that things will just stay the same in the long term, because often there's assumptions made that the modeling won't change too much, but sometimes things like acid mine drainage take a few years to actually kick off, and then you've got a different situation once the initial conditions have moved, and that isn't always very easy to account for. So you really need to monitor things for quite a long time if you're looking at active or past remediation efforts and ensuring that things aren't changing too much. Linking back to cobalt, I think you want to be ensuring that if you do have exposed rocks that have cobalt or other potentially deleterious metals in them, there's obviously those questions around not having too much exposure of things like rainwater or spots where they can leach out into surrounding waterways, because you might not just be leaching dissolved material, you could also be leaching out some nanoparticle material as well. So it's been hard to track in the past, but we're getting to a point where we can actually do that somewhat better with some of the new techniques on offer. So I do wonder if we'll be seeing more of these in environmental geochemistry and remediation toolboxes moving forward as the techniques become more readily available and hopefully a bit cheaper as well. Of course, has to be fit within a budget. You can't do it if it's going to cost far too many thousands of dollars per sample, but there's a lot more that we can learn about how to see where these elements might be found in the environment. And I think assuming the immobility probably isn't the way to go anymore. Most of these metals, you might think that are sitting pretty in samples of oxides or sulfides, but if they start to move, they can form quite different compounds. They can interact with microbes in the area. They can form new species, dissolve, redissolve, form nanoparticles that might interact with other biota in different ways. So it's understanding all these different interactions is more complex than we thought. But I think if there's one single takeaway, assuming that things are relatively immobile is probably not the way to go.
Definitely not. I think you'll find that even though it hurts them, companies could be open to spending thousands of dollars per sample, but it's about the packaging. Why do you need it? And how is this going to impact their there's many different versions of a final mine plan, right? But how is this going to
Absolutely.
impact things? So I think it's about the correct explanations and translating that to companies as to why they might need to do something like this. Yeah. But
Yep.
yeah. And also the having where they can go to have it done, right? Because the companies are limited in the amount of people that they can have on staff and the different specialities. So also,
Absolutely, yeah.
yeah,
It doesn't happen overnight, and things like I think
no.
single particle may become a technique that's added on to the more commercial laboratories in the future, but things like synchrotron radiation are not going to become mainstay techniques of companies, I don't think, and because researchers get a much cheaper deal for these places than companies. Companies are charged full commercial rates to use synchrotrons, whereas researchers normally get subsidized rates of some kind. So that's a collaboration opportunity, but it's not so much one that you're going to be doing straight out. But there are things like X-ray fluorescence mapping now that are being rolled out, and they're much more common to find now from laboratories. You don't need a synchrotron for that, or the resolution is not as good. But if you're looking at things like oxidation state by synchrotron, which is something we also did in this study that haven't actually mentioned too much yet, but that was another thing that we found was that there's cobalt 2 plus and 3 plus in different samples, and you can analyze the oxidation states by slight changes in the spectra of the cobalt peaks as you pass different energy X-rays across it. So we did find the different oxidation states of cobalt were both being present, sometimes in the same sample, sometimes only one of them was there. But that sort of material you're not going to be finding in commercial closure plan information just yet. But there's some things like single particle ICP-MS that perhaps will become a bit more prominent in the next little while. But it's still asking the right questions, as you said, and then not just spending money for the sake of it. It should be spent with the idea that we actually do have questions we want to answer about this, and we're not just doing our whole rock or whole water geochemistry just because we should. It's because there is a question that can be answered by doing that.
Yeah, sure. I guess both in the research sense, but then really in a more commercial sense, because we're talking so much about it. Cobalt, 2 plus versus 3 plus. Is there anything that makes one or the other more detrimental than the other, or is it just something that's nice to know for now?
I'd say 2 plus is definitely more of a detrimental one. If you have that in dissolved form, it's one of those potentially toxic elements to the environment some way. It doesn't normally get released in the amounts that would cause it to become so like that. Unlike, say, something like arsenic or lead, you've got those classic famous pollutants, but cobalt 2 plus is definitely the one that could cause environmental risk if there was enough of it in a place that then gets released in some sort of waste outflow with dissolved cobalt 2 plus. Cobalt 3 plus is typically pretty insoluble, so it's normally going to be found in your oxide or oxyhydroxide phases, maybe with manganese, maybe iron, maybe by itself. But then we've found that you can definitely cycle these things around, and even in 3 plus, it may not stay there quite as long as you would have thought. It's not fully immobile. It could be reacted or could form a nanoparticle over weathering, then get released back and reduced down to cobalt 2 plus, in which case it might become more of a problem again. So definitely cobalt 2 plus is the one to watch out for.
So interesting. It's just, you wanted to say, oh, it's all cobalt.
We'd like to, and too many regulations often have. There's just, you go to
Yeah.
old water regulations and it's like cobalt and then manganese and iron and copper, and they're just there as single elements. There's nothing about the oxidation state, nothing about what form it's in
Mm.
otherwise. Just here's what it is. Is it dissolved? Is it total? Is it dissolved plus solids? It's often very hard to tell what they were even measuring for a guideline.
Yeah. I guess you can maybe tie it a little bit back to limiting techniques. I mean, we take it for granted, but only in the history of us doing soil science, we haven't been able to even analyze for this many elements, no less now start to take individual elements and get different oxidation states. So, yeah, this is all very cool.
Some of it, you're right, it is very recent to get the level of detail that we can get, but it's still often, I think, very patchwork. We have a few different sites where we've done some really good work across the world, but there's many more that we can work on, and understanding that we can add in heaps more detail of interest for elements like cobalt, but probably many others too. There's a lot more stories to be told.
Love it. So let's go a little side quest, which we started about talking in your T section, but Tasmania and Mount Lyell. You've been involved in quite a bit of work around Tasmania's mining legacy, including Mount Lyell. How does understanding metal speciation and nanoparticle behavior help us better evaluate complex systems like the Macquarie Harbour?
I think knowing some of these newer techniques that can give us the information that we didn't previously have does add to the picture. I think it's really hard to get complete pictures of any one site. As geochemists, we know we're always making models. We're not necessarily able to get a complete picture anywhere. There's always a bit more data we'd love to have, but it's something that we can definitely get more information about for nanoparticle phases in environmental geochemistry environments. That'll tell us a bit more about what's going on in the local scale down at the nanoscale, compared to just having that micro scale at the smallest. Now we have a bit more information about what nanoparticles are being found in these samples too. Are they pyrite? Are they oxides? Are they something else entirely that we didn't otherwise think about? This kind of information can add on to help understand the picture of what's happening at the cycling level, coupled with perhaps understanding a bit more about what microbes are living in these environments and what interactions are occurring here. It's one of these sites where you've got the seawater coming in from the ocean, you've got freshwater coming down to this mixing zone mixed with the mine waste that's there. It's really quite an interesting spot in that regard. There's been plenty of research done here in the past and setting the scene, trying to understand the scale of the problem. A lot of it performed by University of Tasmania researchers from past and now still into the present. It's a site I've been working on quite a bit since I got here a few years ago now. And we take our third year students there each year as well to do a yearly water survey down the Queen River from Queenstown down to the harbour and look at some of the sediment banks in the delta and see what's happening and any changes that might be occurring to the sediment that's essentially is formed by mine tailings. So you can dig through the oxidized layers and find the reduced layers, but often it looks a lot more like a layer cake than you'd expect. You think it'll just be oxidized, reduced, but you've got oxidized, small reduced, oxidized again, more reduced. So it can be quite a dynamic environment, even in areas where you might think it'll be relatively simple, but it's much more layered than you would expect, and they have to figure out reasons why that might be the case. Yeah, really interesting to study these sites and looking at the big picture of what's going on, but also the picture of what's happening for your more minor elements like cobalt that may just be really important parts of the system. The pyrite at Mount Lyell contains trace cobalt in several hundred part per million approximately. Some samples from some areas of the mine have less, some have more, and of course in the mine waste environment like this, it's all mixed up, and you've got pyrite reforming at times. You've got the biotic pyrite forming again that can be formed by microbes, and that can then lead to new generations of pyrite in the Macquarie Harbour sediments as well. So one of these environments is just such an interesting place. It's a shame that it exists. Like, I'd much prefer that it didn't exist, but it's one that we have some opportunities to work on and potentially actually look at cleaning up and stabilizing it more and helping to pay for what's there a little bit more by looking at the metals that are in there. But finding the funds and the support to do that kind of work is such a big challenge, because it's an environmentally sensitive site, and there's always that risk of doing something can be more harmful than doing nothing, but doing nothing equally is not that sensible either in this case. But that is what's been done, if doing nothing is what you can do, for the last 100 years. So it's one of these really interesting but challenging sites that we have in Tasmania.
I always love the perspective of geoscientists, where we find things that are interesting, but are also, in this case, perhaps quite terrible, right? It just reminds me of when I lived in Chile and how I just found every earthquake to be like the coolest thing, right? I felt very safe there, I guess is a bigger point I should make, but just being like, oh my God, this is the cool, you'd be in the middle of an earthquake and you're like, this is so cool. But it's the perspective of a geoscientist. And so I just find it in this case too, things that we find fascinating, the layer cake kind of thing. And I'm thinking, oh, is this seasonal? Is this something? And it's just like, number one, to most people, that's not even remotely interesting, but it's also interesting on a level that's a bit detrimental, a little bit sad. Because we don't want it to be there. So
don't know exactly what the causes of those kind of things are. And I think I've been out to that harbour now, must be quite a few times, probably 5 or 6, I think. But I think only one time I went out there and it wasn't sideways range. It's a hard place to work as well. You try and dig a trench and it just gets filled up by rain as quick as you can dig it. And you're like, okay, back off, because there's a risk of lightning over here from this. You could see some interesting clouds forming and you have to get going. You don't want to be out on a delta with a shovel in a storm. So we've had to retreat quite a few times. It's a pretty wild place out there. So it's always got the safety first. So you just head back and you come back a bit later. Yep, no, you're not going to risk getting a sample for. I've never seen lightning there, fortunately. As it's similar, perhaps to the earthquake story. But you don't want to give it the chance of finding out. Could this be that one strike? No, we'll do this. We'll dig this hole later, and it's also often the final site on our third-year field trip. So it's people getting a little bit more tired by then, and the ability to stand in the rain for another few hours is not quite as high as it was in the first part of the trip.
I can't think of anything more miserable.
So unfortunately, often what weather's like out that part is just, I think it's roughly 270 days of rain per year for that part of Tasmania.
Oh my goodness.
So it's 3 in every 4, and late winter, early spring when we go is one of the wettest periods. So it's just an unfortunate part of the teaching timetable.
You might want to switch that. Switch the course.
Would actually be the best reason to do it would not so much be for any other reason except just check what's happening a bit more in the other times of the year, going out at other points. So we have done some other studies at times, but the yearly check is always when it's at its wettest. So it's be quite different right now compared to what it is 4 months ago, I'd say.
So there would be some noise in the data. Good point. Love it. Look, so you've done some similar work on tellurium biogeochemistry, another critical but also poorly understood element. Are you seeing some common themes emerge in how critical metals behave at the Earth's surface? And perhaps just in particular, you can comment on tellurium.
Yeah, definitely starting to see some common themes. I think the reactivity, mobility aspects are often greater than we expect. For tellurium, it was not oxide nanoparticles we were finding, but we're actually finding nanoparticles of tellurium itself. So essentially elemental tellurium, or if it was a mineral, it'd be native tellurium. And this had been predicted by laboratory experiments from as far back as 1914. There were some studies about if you put tellurium into an agar plate with microbes, it turned black. And the reason for that was that you're getting elemental tellurium forming. But until the last few years in my work, no one had found those nanoparticles in nature before. So it wasn't something that had ever actually been proven to happen in nature. It's just a nice curiosity in the lab. And then it had quite a few applications in terms of understanding tellurium mobility, at least in microbial sense, but actually finding them in nature was not something that had been done. We just found microbes that could reduce tellurium from tellurium 4+ or 6+ oxidation states, where it forms these what we call oxyanions, so essentially tellurite, tellurate. So it's just a sulfate or a nitrate, but with tellurium and oxygen instead. And there's microbes out there that can reduce those. They're quite toxic in themselves, actually, as well, interestingly, reduce them down to elemental tellurium, which is both helps detox, but also transforms the element from one form to another. And these nanoparticles themselves still quite reactive and have interesting behaviors of their own. I know in some microbes, it seems that actually they make always needle-like tellurium nanoparticles, and they precipitate them on the outside, and that can actually be quite a helpful thing for them potentially, because that makes it a bit harder for anything else to get in and attack the microbe itself. So you've got these little needle plates on the outside, but other microbes put their tellurium on the inside of their cells when they make these nanoparticles. So it's quite interesting how this can all happen. But that's all from, in a sense, other more lab-based studies, but we were able to find them in the environment in a similar way to, as I described, the cobalt. They were, by single particle ICP-MS techniques, we could analyze how many tellurium nanoparticles were being found in different soils from around very tellurium-enriched sites. It's a crazy place out in Mexico that's got roughly 0.2 weight % tellurium in the ore there, so it's ridiculously high compared to what normally you might find tellurium at, which is a high tellurium grade, probably in a high sulfidation, might be, let's say, 200, 300 part per million tellurium, but this was another 100 times above that. Pretty ridiculous kind of place, but a great place for field work and really exciting one to do some work on. So for tellurium, again, yeah, reactive, mobile, and amazing transformations from different oxidation states. So we're seeing these parallels around from tellurium, from cobalt, and I'm guessing from many other elements too, particularly the redox active ones. And there's just all these questions about how they form from one mineral to another, how microbes might be involved in surface environments. I think there's a lot more interesting work to be done here about how they move around the environment and then translating that to the environmental mediation, mobility kind of stories to help sites that have had tailings dams that have these elements in them, make sure that they're made safe and aren't going to have any releases to the environment in any way, as long as there's not some major breaches of any sort like that, then most of these places will be doing pretty well. But it's important to know what's happening with the elements in the environment, and that can both be helpful for exploration and remediation activities.
Watch this space. It's so cool. It's so, for me, a little bit random to be talking about on a Thursday. I love it. Is it a Thursday or is it? I guess you're a Thursday.
It's a Thursday for me. Yep, it's absolutely
a Thursday. Okay, so we'll call it Thursday.
It's always Thursday somewhere. No, maybe not in that case.
Right.
I did around New Year. It's almost moving around. You can go celebrate New Year across different parts of the world, and
yeah, you can celebrate it twice in some places.
Exactly.
Once is fine for me. So if there's one assumption about metal behavior in surface environments that you think geochemists, regulators, or mine planners still get wrong, what is it?
I think relevant to this conversation, I think it's that assuming nanoscale is the same as the microscale or the macro scale. I just don't think that's often the case. There's a lot more happening that we haven't really captured that much in these environments. There's a lot more that happens down at that sub-micron scale than we've previously been able to analyze for. And that's not a detractor on past work, just that it couldn't be done, but now it can be done. And that may be an additional tool that we should be looking at to understand what's happening in more complex environments. And the secondary thing to that is that assuming that things will stay the same in the long term, that's probably a poor assumption, but often one that is made. But I think you have to be looking for changes that might occur after, let's say, 20 years of a tailings dam operation or waste rock storage facility. Is it still the same as it was? Has anything changed? Do we need to make any updates to these kind of plans? And I think making a change based on evidence is not a bad thing, but sometimes making any change can be seen as, oh, we changed the initial design. This is a really bad thing, but that may well be required. And that's, I think, being sensible rather than being needlessly reactive, in my opinion, at least.
I think even as we talked about a few, I don't know, maybe 20 minutes ago, like that Cobalt 2 plus is like the bad one, Cobalt 3 plus, no worries. The fact that we can see it in terms of oxidation states as well. I think that's, after following this conversation, I feel like that's something that's really important too, because you could be making decisions based on certain elements that you're afraid of causing one problem or another, but really we actually don't have to worry about this element, but really it's this one that's actually going to be problematic. And I think that's pretty powerful.
Yeah, and it all comes back to ore body knowledge again and knowing what's in your tailings dam in that case. So it's that all these questions do link back up, and yeah, I think there's some really exciting things and really interesting things that we'll be able to see as we have better techniques to work on them.
Yeah. Oh my gosh, this has been so great. Thank you so much for joining us, Owen, on GeoChemistry. I think that this conversation just really highlighted how much we still have to learn about these critical elements, critical metals, minerals. I hate when they call them minerals, but anyway, whatever you want to call them, it just highlights how much We still have to learn about how they behave in surface environments, which is where a lot of them are going to end up in this case, and why looking beyond bulk geochemistry down to mineralogy and to the nanoscale will matter for both mining and environmental decision making. If you guys want to learn more about Owen's work in environmental geology and critical metals research at University of Tasmania and Coes, we'll have links in the show notes. And for all of our listeners, let's just keep asking better questions, keeping these conversations grounded in data. And of course, always make sure that the tea's hot. I want to thank our sponsor, LKI Consulting, and It's Water and Coma Media for our music. I'm looking forward to chatting with everybody next month.
Thanks so much for having me.